It's a pleasure to have Govind as the young speaker today. Govind was supposed to be here, but I think he got enough sun or he knew that he's going to get enough sun in Sweden, so finally decided not to.
He's going to get enough sun in IMS.
In person, huh? Or he got enough sun in IMS. Okay. Govind is a postdoctoral researcher in Uppsala University in Sweden. And prior to this, he was a postdoc at IIT Bombay, and he did his PhD from. He had a joint PhD from CMI and University of Bordeaux. Particularly from Lebris, I believe. And today he is going to talk about generalized timed automata. So, Govind, yes, you can start.
Yeah, thanks, Shubhashish. So I would first like to thank the organizers for inviting me for this talk and accommodate me being online. Okay, so the talk is going to be about formal verification of real-time systems and a new approach, essentially a different approach to the formal verification of real-time systems using a new model called generalized timed automata. So this is joint work with Akshay, Paul Gasta, Aniruddha, and Srivatsan. And okay, so let's start. Yeah. So the talk will be structured as follows. I'll first try to motivate why we are interested in this problem. In particular, what is model checking? And then I will give a brief overview of timed automata for people who are not familiar with this model. And then I will look at some challenges in model checking for real-time systems that people have been looking at, and my work in the context of these challenges. Okay, so what is formal verification? So I guess most people will know this, but we are interested in checking whether systems are correct. So what do we mean by this? We work with a lot of cyber physical systems, hardware, software systems every day. And many a times we say that there's a bug in our laptop or mobile phone, but these are minor inconveniences. But many a times we are working with systems like controllers in nuclear reactors, components of spaceships, or integrated circuits, which are safety critical. So any erroneous behaviors in the systems has the potential to cause large-scale loss in life and property. And therefore, it's critical that these systems behave correctly at all times. And formal verification is an area that tries to address this problem. So what we do here is we try to formulate this correctness requirement as a property, and we ask whether the system satisfies the property. Right. So while there are several ways to address this, like you could do exhaustive enumeration of exhaustively exploring all possible behaviors, testing, simulation, etc. One of the most successful techniques in this area is this technique called model checking, where what you do is you take a finite formal description of the system, typically given using an automated model, and the property, which also need to be stated in a very precise and formal way, which is typically specified using a logical formula in some logic. One of the most popular such logics is what is called this linear temporal logic. And an example of such a property is like, okay, every request, this is a property formula given here, which essentially translates to every request A is followed by a response B, right? So many a times you could be working with models where your local machine is interacting to a server sitting somewhere else. And it's a very reasonable expectation that you would expect a request issue to be met with a grant at some point of time in the future. And that is what this property says. And this could be one correctness property that you're interested in. And here a model is expected to satisfy this property, right? This is what the setting of model checking. Okay, but what does the model checker do? It takes the model and specification as input, and it either tells you, yes, the specific it is satisfied, which means that every behavior of the model respects the specification, or it tells you there is a violation, which means that there is some behavior of the model that does not respect the specification. Okay, but how does the model checker typically do this? So we are interested in the behaviors of the model, which is given by the language of A, the automaton that models the system, and the set of all behaviors that respect the specification is given by L of I, the formula. And we are essentially asking, it's the intersection of these two languages, L of A and L of I complement is empty. And what a model checker typically does is it takes the negation of the formula that we are interested in and converts it into an automaton. And then you are model checking essentially amounts to analyzing this network given by the model and the negation of the automaton corresponding to not phi. Okay, so but this technique has been very influential in the area of formal verification, just evident from this Turing Award of 2007, which is awarded to Edmund Clark, Emerson, and Sifakis for their pivotal role in developing model checking. And this is also the backbone of several industry-strength tools such as Spin, NewSMV, Uppal, and many more. But the key takeaway here is that this depends on this efficient and having an efficient translation from logic to automata. And this is a key challenge that I will talk about later in this my talk. But this was model checking in the context of untimed systems, which has been studied over several years. But our focus is model checking for real-time systems. Now here, the system is modeled using an automata, but there are several choices for this automata model. There could be timed automata, automata with timers, even clock automata, all of which I will briefly give a quick overview about to give an intuition of what they are. And for logic, you would expect to have a real-time timed analog of this any of the classical logics, right? So I will talk about both the aspects of model checking for real-time systems next, and then I will talk about why our work is relevant in this setting. So let's first look at modeling, the first aspect of model checking, which is modeling. So let's look at this simple language, AB star, where any two letters, consecutive letters, are separated by the time interval 1. Okay, and here is a timed automata that captures this language. So this is the most popular model for real-time systems. So what you essentially do is you have what are called clocks, which are real valued variables. And using clocks, so you take the first transition on A for the first letter. And then after that, every time you see a letter, you essentially check the time elapsed between the last position and the current letter is exactly 1. Right? And then you reset X to 0. And this way you enforce this constraint that time elapsed between any two consecutive letters is 1. Now, I will go into what timed automata is in a bit more detail in a later part, but just to say that there's a model called timed automata, and the state-of-the-art techniques for timed automata require symbolic enumeration, but the caveat is that this symbolic enumeration does not terminate in general, and one needs some special techniques to ensure termination of the reachability algorithm for timed automata. This is just to say that there is a model called timed automata which has this property. But then here is another model called automata with timers. So what you have is what are called timers, which can be set to an interval. So here you can see that Tx is set to the interval 1, 1, Ty is set to the interval 0, infinity, where it's non-deterministically set to an interval, and then it counts down till it hits 0. So this is typically what you do with a timer in your phone or whatever. So you set it to a value and it counts down to 0. So here what you do is upon doing the first transition, you set Tx to the interval 1, 1, exactly 1. And whenever you see a letter, you keep asking whether it has timed out, which means it has gone to 0. This way you ensure that the time elapsed between the two letters is 1. Just to say that there is another model called automata with timers, which was in fact introduced even before timed automata. And the very surprising and interesting property is that symbolic enumeration was possible here, and it is guaranteed to terminate. You don't need any special techniques to ensure termination. But over the years, the focus has shifted to timed automata because apart from some technical conveniences in developing reachability algorithm, this allowed for a very easy way to characterize determinism, because in timed automata, it's easy to say when your outgoing actions are deterministic. But just to say that over the years, the focus has completely shifted to timed automata. And while there's a rich theory and several tools to handle clocks with timed automata formalism, there is no real tool and definitely not much work done on timers. And the reason why we're interested in timers is most of the benchmarks that you see from industry, for instance, automobile industry, etc., use timers extensively. The engineers, they like using timers extensively, and it's often very difficult to go from timers to clocks because it induces a blow up. So our first motivation is, can we allow the people modeling systems to allow clocks, timers, etc. freely? to allow more freedom in modeling. So can we reintroduce timers to model real-time systems? So this is one motivation. Now let's look at the second aspect of model checking, which is specification. So what are typically time properties that you would want to check? I mean, you would want to say that some event occurs within 100 time units, or the time elapsed between any two events is some less than 5 time units, or so on. So I will talk about two possible formalisms that people widely use to model. One is
a question. So when you say it like the symbolic thing doesn't terminate, do you mean that, so do you consider regions as symbolic thing, like a region graph as symbolic?
Yes.
But
I was talking about zones. Okay, I should clarify. I was talking about zones.
Usually terminate, right? I mean, it's the zones.
Yeah, regions are guaranteed to terminate, but they are notoriously bad because it's exponential and so on.
Okay.
I just wanted to say the zone-based techniques which were developed for both. In one it terminates, one it does not. Okay. Yeah. So coming to specification part, so there are two possible formalisms. One is an automated model which can directly capture specifications, which is called event clock automata, where you have two special clocks associated to every letter of the alphabet. You have an event recording clock, which stores the time since the previous occurrence of the event, and an event predicting clock, which stores the time until the next occurrence of the event. So using this, you can easily say both the properties that I say here, right? You can say time elapsed between last day and next day is 5 very easily. So this is another model that we are interested in, but again, there is no tool that works for this, and indeed no efficient algorithms that complete algorithms that were developed for this. So we would want to address this. And more interesting is this timed analog of linear temporal logic, which is called MITL, where you can say properties like this. So earlier we saw that every request is followed by a response. Here, in addition, you can say that this response should be within 3 time units. And if you think about it, it's a very natural expectation that you don't want to wait an indefinite amount of time for the response. You would want bounded guarantees for when you receive the response. You can say things like this using this metric interval temporal logic, and this is the logic we are interested in. So this is the picture. So you have several models, several formalisms for modeling, and again, multiple formalism for property. Again, most interesting is the metric interval temporal logic, and we want to have an efficient way to model check this. This thing. Again, so what you would want to do is you take the formula in MITL and you convert it into an automata, and then check reachability in this network of automata. So it involves two key steps: efficient translation from MITL to automata, and then you would want to have efficient reachability algorithms for this model. But this begs the question, to which model, right? To which automata? And what would be very useful is the following. So if you have a model which takes care of modeling in the sense that it captures all the widely used formalisms, timed automata, automata with timers, event clock automata, all the things that we talked so far, plus a direct translation from MITL to this model, whatever this new model is, then we are done, right? Then model checking is essentially analyzing this model. So then this would be very useful. And indeed, this is what we propose in this work, which is the generalized timed automata, which is a framework that unifies these various time models that I talked about so far. So what I mean is like, one takes care of models and not just captures all the models, it allows us to use the features of all these models simultaneously. What I mean is you can use clocks, timers, event clocks, everything at the same time in the same model. And it also allows you to put constraints between these features very freely. So that way it's very general. And then we also propose a direct translation from this metric interval temporal logic for any metric interval temporal logic formula to this generalized timed automata. And while doing this, we also propose efficient techniques comparable to state-of-the-art techniques for timed automata. So we are going to a more general framework while not losing much in terms of algorithmic efficiency. So this is somehow the summary of this talk, which is we capture models, we take care of specification, and we have efficient algorithmic techniques. And I will go into each of them one by one, but this is the take home for this talk, I should say. Okay, but before going into what this new model is, I will give a quick overview of what timed automata is and what is the state-of-the-art techniques, how reachability is addressed in timed automata. So if there are no questions, I can go into timed automata. Okay. So these are just basically finite state automata equipped with real valued variables called clocks. So you have finite set of states, finite set of transitions. Additionally, you have finite set of clocks. So these are variables which are set to 0 initially, and they increase at the same rate. Now, associated to each transition, you could have what is called a guard or a reset. So the guard x greater than or equal to 4 here basically means that this transition can be taken only when the value of clock x is at least 4, right? And the reset y setting to 0 basically means that whatever the value of clock y, when you take this transition, upon taking this transition, it goes to 0. So this will become clear when I look at a run immediately. But okay, a configuration of a timed automata is a tuple containing a state and a valuation, which maps clocks to non-negative real values. Okay, let's look at a run of this timed automata. Okay, you have the initial state T, and where both clocks are initially 0, as I said, which is the initial valuation. Now you want to take A, you need value of clock x to be at least 4. So let's say you lapse 5 time units, and now both clocks have gone to the value 5. From here, you can do an A because you satisfy the guard. But now you get x equal to 5 and y equal to 0 because you reset the value of 5 to 0. Then you can elapse 3 time units because you need have the guard y greater than or equal to 3 here, and then go to state Q, and then take the transition B to reach the accepting state R, and so on. Right? This is a run of the timed automata just to give a feel of what configurations and runs looks like. And the reachability problem is essentially asking whether the automata has a run to an accepting state. And this problem is known to be p-space complete. So it is a very relatively hard problem. And next, I will try to give an overview of what is the best reachability algorithm that we have for timed automata, give an intuition of what we do there. And as you can see, clocks take non-negative real values. So to have any hope to have, sorry, yeah.
So the guards must be pretty limited. So like, can you like, so the guards are all just inequalities against fixed numbers.
Inequalities against integers, but what I have not added here is a guard of the form comparison of clocks. So x minus y greater than or equal to c. You can use that as well.
Arbitrary things that you can just do a Turing machine with, right? You can just think of each clock as a full tape.
Sorry, can you repeat?
So like you can just think of the whole clock as the tape, and like each bit of the real number as one cell. So that's why the guard and reset both have to be fairly limited. To
Yeah, the operations are pretty limited, but it comes into play. I mean, the more behavior comes into play when you can when you reset a clock, the difference between the clocks changes, right?
yeah.
Yeah. So then you have somehow more behavior coming into play.
No, that's fine. But I was just wondering that like if you are if I'm allowed to do everything, like I'm allowed to reset to arbitrary values, if I'm allowed to basically look at so okay, so the reset is only to 0, no other values allowed.
In this particular, the basic model of timed automata, it's to 0, but there are extensions which allow update operations, which allows you to update to a fixed value.
Because the thing I was wondering is that if you allow reasonably powerful bits, then it's as powerful as Turing machines, right? Because
Yes. This is what I'm going to. You will see this later in the talk.
Okay.
It's true that updatable timed automata are reachability problem is undecidable.
Okay.
Yeah. Sorry.
That was what I was wondering about. So
Okay. Yeah. Yes.
Turing machines because
Yeah.
real numbers
But in this basic model, we allow resets only to 0. So okay, but to have now next I will talk about this reachability algorithm, and to have any hope of addressing the reachability problem, you need to have some way to handle this uncountably infinite set of valuations. And this is the first step, which is symbolic enumeration of configurations, which is called zones. So I will not go into technical details of what zones are, but I'll just try to give an intuition of what they are. So these are sets of valuations which have very concise representation. So which is comparison of clocks compared to a conjunction of constraints of the form, comparison of clocks compared to an integer. Right? An example is this. So this is a zone. The set of valuations captured by these 3 constraints constitute a zone. Right? And the standard reachability algorithm does an enumeration of zones essentially. which I will briefly try to give an intuition of using the simple automata. So you do an A, go to state Q1, and then you keep doing B every one time unit. So let's look at what the initial zone would be, so initially all the clocks are 0 and they increase at the same rate. So the difference of clocks is 0 at this point. And so you have this configuration Q0 with y minus x equal to 0. So this is the initial zone. And upon doing an A, you go to the state Q1, but you reset x and y at the same time point. So the difference of clock does not change. So y minus x is again equal to 0. Right? But from Q1, when the value of clock x is 1, x is reset to 0. But then you can again elapse time. So you get this next zone to be y minus x is equal to 1. Then again, at the next after one time unit, you can again reset x when x total time elapses 2, and you get y minus x equal to 2, and so on and so forth. So the graph obtained by this symbolic, this enumeration of zones is what is called zone graph, where your configurations are state, comma, zone. And so this somehow deals with the uncountable infinite set of valuations by looking at sets of valuations. But then there is still a problem that this symbolic and this enumeration does not terminate in general, as you can see here. You can have larger and larger differences constraining the difference between clocks in general. So this is the last, yeah.
In this particular example, I mean, the clock y is of no use, right? I mean, you could have just...
Yes, it's a dummy clock, yeah, which I added to demonstrate this behavior. That is true, yeah. But in general, you could have arbitrary difference between clocks, and you can always use y later, right? Yeah. So the last missing piece is you need some way to ensure that these graphs the exploration has to terminate, right? And this is typically done using a simulation between valuations. So what we mean is we need to have a finite abstraction of the zone graph, and this what we build. We motivate this using the simulation between configurations, which is then lifted to zones. When I say simulation between configurations, we mean that whatever you can do from one configuration, you should be able to do from the other configuration. Very natural notion of simulation. And at a very high level, what we do is whenever we see a new zone, we ask whether does there exist an already seen zone such that anything that you can see from this new zone, you can see from the already seen zone. If yes, it's very natural that you don't gain anything from by continuing exploration from this new zone. So you stop exploration from this. On the other hand, if there is some behavior from this new zone, which is not possible from any of this already seen node, then it makes sense that you have to continue exploration because there is a potential of seeing something new from here, right? And this is this notion of simulation for zones, which, and there are several well-studied simulation-based abstractions which produce finite zone graphs. And this is still an active area of research. And the goal is to obtain smaller and smaller zone graphs by developing better and better simulations. Okay, this is the single shot picture of zone-based reachability. So you have zones, which are symbolic representation of configurations. You have a simulation relation between configurations, which are then lifted to zones, plus an efficient simulation test. I forgot to mention this. You will have to do this comparison several times. So it's very crucial that you need to have an efficient simulation test. And finally, we prove termination by building a finite abstraction based on this simulation relation. So this is the big picture, single picture of this reachability algorithm. I give this picture because I will talk about, I give a similar picture for the GTA model later. So just to give a context, right? So this was this notion of idea of timed automata. Now I will try to give an intuition of what is generalized timed automata is. How do we obtain this? And how do we obtain this model essentially?
So there is a question.
Yeah.
Can you give an example of this algorithm for the hard example you described before?
You mean this one, the
y minus x.
Right. Yeah. So here it's basically this. So you see this the most primitive example of such a simulation would be that we note that the only constant, the greatest constant that you care about in this automata is 1.
Okay.
Right. So you really don't care when the value of y minus x goes beyond, let's say 1 or some let's say 2. There is no interesting behavior that you can distinguish from when the value of this maximal constant is when the difference goes beyond the maximal constant.
Why is that? Because even though x is small, y minus x should be very large.
Right. So y minus x could be very large, but you cannot distinguish that the y minus x is larger. It doesn't make a difference whether y minus x is 100 or 1000, right?
So
You
what
cannot
is
distinguish.
The cards that are there, they only care about this difference of one.
so what you can do with y minus x equal to say 2 and what you can do with y minus x equal to 200 is the same kind of behaviors that you can do. That's what he's trying to say.
Exactly. You cannot distinguish. Yeah, exactly. Yeah.
How would you formalize this? What is the formula you would say to this?
So
Sorry.
the question is, how do you formalize this? How do you formalize deeper system?
Right. So you have this notion of it's actually called maximal constant abstraction, which basically looks a static. You do a static exploration of the timed automata and look at the maximal constant, and then whenever you do zone-based exploration, whenever the constraint between two, so zones are basically conjunction of constraints of this form, right? Whenever this difference between goes beyond this maximal constant, you just replace it by the maximal constant. Thereby, you get only finitely many zones now because your set of constraints that you can use is coming from finite set. Did it answer the question?
I'm still not sure. So my question was, suppose that you have this largest constant in your graph. You're saying that this implies you only want to consider a finite number of zones. But
yeah,
I don't see the proof of this, or I don't see why why are the other zones sort of equivalent to these finite sets that you have?
right. So essentially, the proof of this goes through this notion of what are called regions, which are basically sets of valuations which are bisimilar. In the sense, you look at configurations which can simulate each other, and it is like this is what Sibachi was talking about earlier. So there are guaranteed to be only finitely many regions based on this maximal constant. But it's a large number. It's exponential in the number of in the maximal constant. And what we essentially show is if you apply this, if you do what I said, which is replacing the constraint between clocks by the maximal constant, when it goes beyond maximal constant, you can show that downward closure of these zones is a union of regions. And because the regions is finite, it's exponential in the number of regions. You can only have that many zones. So while it's true that the number of zones could be arbitrarily, it could be extremely large, which is exponential in the number of in the maximal constant, you can show that it's finite.
Okay.
Yeah. I can explain it more offline, but this is just an intuition of how this proof goes. But okay, yeah, thanks. Okay, so now I'll try to give a brief high-level overview of how we obtain this generalized model and why we do this. So we talked about clocks in timed automata. So here what we do is we enrich timing constructs. So instead of clocks, we have two different types of clocks. We have what are called history clocks, which are more or less like the clocks of timed automata in the sense that they start at 0 and they increase with time in the positive, but they take positive values. But you also have this dual notion of future clocks, which start at some non-positive value, and they increase with time up to 0, but not beyond 0. Right? So we have two different types of clocks, and we also enrich transitions. We allow a richer syntax on transitions, both of which I will explain in the next slides. So first, how do we enrich clocks? So we have, as I said, what are called history clocks, where you have the guards are, you can say, ask x lies between 2 and 5, which is exactly what you saw in timed automata, and your resets which set x to 0. So this object, this construct basically says, if your value of clock x is between 2 and 5, reset x. So x is set to 0 if x lies between 2 and 5. And this generalizes this notion of standard clocks and what are called event recording clocks, which we saw earlier for event clock automata. But the more interesting thing is this dual notion of future clock, which is basically ranging between 0 and minus infinity. And guards are, okay, you can again ask whether it lies between an interval, but the interesting object is this, how this clock is modified, which is essentially is what is called a release, which basically sets y, the clock, to an arbitrary value in this legal value range, minus infinity to 0. It's essentially a non-deterministic update. So to motivate why this is, so let's look at this sequence. So it says that, okay, release y, which means non-deterministically set it to a value between minus infinity to 0, and then check whether it lies between -5 and -2. So if you pass this thing, what essentially happens is whatever the value of y initially, you release it, and the second component acts as a filter. So after you do this, the value of y lies between 2 and 5, between -2 and -5. So if you think about it, it's like a flipped notion of a timer. So you predict that y lies between 2 and 5, and then you count up to 0 instead of counting down from 2 to 5 to 0. So this models timers and this predicting clocks. And I would just like to mention that it's crucial that both clocks increase with time, because this allows us to use the zone-based analysis, which allows us to keep the difference between clocks fixed with time elapse. And this is one crucial observation, but yeah. And the other generalization is we generalize transitions. So while in timed automata, you just had a guard followed by a reset, which is quite limited, as you pointed out. Here we allow arbitrary interleavings between guards and clock modifications. You can check for a guard followed by a clock modification followed by a guard, and so on and so forth. The only constraint is that this has to be done without elapsing any time in between. So once you start processing the program, what we call instantaneous time program, which is the arbitrary interleaving of guards and transformations, you cannot elapse time. And if you think about it, sorry, yeah.
So when you write that y in square bracket, what does it exactly denote? I think you mentioned, but could you say
It's an overloading in the sense that if it's a history clock, it's a reset, and if it's a future clock, it's a release.
it's a
Release.
It's a release, the update operation.
Okay.
But yeah, these are just, I mean, I'm just defining the syntactical notion, but I'll give intuition of why this is useful in just a minute. But just to say that if you want to do something in zero time in a timed automata, you would need several states and transitions, right? But here, because you can do several things, collapse several things into a transition, you can do this in a very succinct way in just one transition.
I have a question.
Sure, yeah.
What happens if a future clock hits 0?
Sorry.
What's the-
Yeah. I'm. Your run gets blocked essentially. You cannot proceed with the run. So, but I was going to explain in the next slide. I think a run of the time domain, GT.
And another related question, can you implement future clocks, the same phenomena using history clocks, or are they capturing different things?
You can. You could implement certain features of future clocks in history clock by storing commitments in states, essentially blowing up states, I guess.
Yeah, that's what I
But
have.
yeah, but it comes at a huge blow.
You can't what?
It can be.
It will come with a blow.
Okay.
So why is it so? I mean, this could you give an intuition why the future clock, if you want to implement with the history clocks, then why will it record a blow up? Properties
So-
not easy to.
Sorry.
So what kind of properties? Like I mean, it's much easier to encode with a future clock rather than a history clock.
Okay, so I should rephrase what I said. So you can encode properties of future clocks, certain properties of future clocks using history clocks, but I should say not in its full generality, which will become clear next. So I was talking about a fragment of behavior that we are interested in, but yes, in its full generality of what we just saw, I don't think you can encode it using history clocks, because you would need to keep track of arbitrary large differences, right? So this is intuition of why you cannot do it using history clock. But if you're only interested in certain restricted behaviors of future clocks, this you can do. which is what we are going to be talking about later. But yes, but in its full generality, it's not possible to encode it in history clocks because you would need an infinite number of states essentially.
Okay.
Yeah. But yeah, just to give an intuition of what a run of a GTA looks like. So here is a simple GTA with two transitions. So let's say we start with the configuration where X is a history clock and Y and Z are future clocks. So X takes the positive value 3 and Y and Z are -10, -7 respectively. And from here, you can elapse, let's say 2 time units. Just to illustrate time elapse, you can go to P with X equal to 5 and Y is -8 and Z is -5. All the clocks increase by the same value. Now from here, you can do A because X is 5, which is greater than 2. And then we saw that this release operation followed by this filter essentially sets Y to a value between -2 and -5. And indeed, you get Q with Y set to -3, but the other clocks remain same. Now, to illustrate this point that we just mentioned, you cannot do time elapse greater than 3 here, because then the value of Y would go above 0. So this is disallowed. And then, okay, just to say that you cannot, sorry.
You have Y
No, it
minus.
was released, so it is
Oh.
set to some value.
Oh, okay.
Yeah,
Oh,
Y was released, Y is now -3. So you cannot elapse any time greater than 3, essentially. So I just added this to illustrate this thing. But then you can elapse 3 time units and get Y to 0 and then do B. Just to say that. But the take home from here is basically this. So what we are doing here on A is that you're guessing Y, you're releasing Y and setting it to an interval -2 to -5. And then you are checking, when you see a B, you're checking Y equal to 0. So essentially what you're doing is in the first transition, first part, you're setting Y to an interval I. And then you're validating the guess. So essentially you're predicting that something is going to happen in I. And indeed, in the second part, you are checking that your guess was correct. So is it essentially for the first part is making a prediction, and second part is validating that prediction, validating the guess. So this is what is the most important takeaway from here, which I will require in a later part of the talk. But this is all we need to know from this notion of GTA.
How is it valid? Yes, even if 5 was -1, nothing would change, right?
So if Y was -1.
Yeah.
Sorry, I didn't get the question. Can you repeat?
Validating the guess. What does it mean to validate the guess?
so what is meant by validating the guess? So what do you mean by?
Right. So if Y is -1, you would not be able to take this transition. Right? This transition can be taken only when Y equal to, it's a guard, Y equal to 0.
No, I will take it after delta equals to 1. Just like you take it to 3.
Right. So you can take it only when Y equal to 0. You can, of course, when Y equal to -1, you have to elapse some time and then take it. So essentially, you're saying the time elapsed between this point and when you are checking a guess is lies within the interval I.
Okay.
Yeah. And this is this notion that we will use later. This is why the future clock business is interesting. Okay. Right. So next, I will try to motivate why reachability problem of GTA is hard. And yeah. So here is a GTA with has two history clock X and two future clocks Y and Z. And let's say the program 1, so the form X equal to 0, and you have Y being set to Z -1 and Z being set to Y. Just I will try to motivate what a run of this GTA is. And the initial configuration is X is of course 0 and Y and Z are, let's say, are initially 0. So from here, X equal to 0, Y equal to 0, Z equal to 0, you can do A any number of times, right? And when you're doing A, you're checking that X equal to 0. So you're not allowed to elapse any time because it's a history clock. X has to be 0 always when you're in Q0, because whenever you're doing A, but then Y, you are releasing Y and setting Y to Z -1, which since Z is 0, you're setting Y to Y -1, and then you're releasing Z and setting Z to Y. So upon doing 1A, you go to X equal to 0 and Y and Z set to -1. Now, upon repeating the A one more time, you will go to y and z being set to -2. And upon doing this n times, you go to y and z being set to -n. So now let's say you're done with A's, you start doing B's. Once you take this transition, but the transition on B basically asks that X has to be 1. So you need to elapse 1 time unit. Okay, but note that the value of Y and Z are -n after you do n A's. So you can elapse at most n time units. You cannot elapse more than this. So, but then you can keep doing B's every 1 time unit, but how many B's can you do? You can do at most n B's. So long story short, the language that's accepted here is A power n B power m, where m is less than or equal to n. And already you can sense that something bad is happening because this is not even regular, right? So this is just to motivate the next thing, which is the reachability problem for GTA is undecidable in general, because you can easily encode counters using these future clocks if you allow full power, and you can encode a Minsky machine, a 2-counter machine using counters. How we do this is we can for each counter you can store the negative of the value of the counter in a future clock YC for a counter C, and you can encode increment and decrement operations like this. I will not go into how we do this, but just to say that we can encode this. Okay, so we motivate this nice new model, and then finally we say reachability is undecidable. So what is the whole point? So when we look at how we encode this 2-counter machine, we are able to identify that the source of undecidability is this one diagonal constraints. What we mean by diagonal constraints is constraints between clocks. So here you have a constraint z equal to yc plus 1. So you're constraining difference between two future clocks. So the bad behavior is being induced by these kind of constraints and arbitrary release of future clocks. When you're releasing this clock z, you're not checking for anything. You're not checking the value of z so far. So just to say that this bad behavior is arising because of this unregulated behavior of diagonal constraints and release of future clocks. And to recover decidability, what we do is we put a blanket restriction on how this interaction happens. We basically say that you can check difference between two future clocks only when these value of future clocks are either the special value 0 or -infinity. So if we impose this restriction, it turns out that we are able to recover decidability. And moreover, the important thing is that this is not really a restriction because it captures all the models that we're interested in. Vacuously, it captures if you don't have this comparison constraint between clocks, it captures that. But moreover, it captures timed automata with these constraints, even clock automata with constraints and automata timers. So it captures all the models that we're interested in. So even though we have to consider restriction, it's not really a restriction because it captures everything that we're interested in. And this is how we recover decidability. And finally, before going into this logic to automata translation, I'll try to give a intuition of how we do zone-based reachability. I think it's not very interesting to look at this, how we get GTA zones, which require a lot of technical machinery, but we have analogous notion of zones to GTA zones. We lift this to notion of GTAs. But the interesting part is how do we get termination? Because in timed automata, what we did was we used simulations between configurations for termination. But the bad news is for GTAs, we do not have a finite simulation between configurations. And this is essentially arising between future clocks. And I will just try to give a quick example to motivate why this is the case. So let's look at this GTA with a future clock X and a history clock X and a future clock Y. So in this automaton from the state L1, you keep doing B every 1 time unit, and finally you can take C if X and Y are 0. Let's look at two configurations with state L1, but where one value of Y is -n and the other value of Y is -n. Now, as has been the theme in this talk, you cannot elapse time more than which forces future clocks to go beyond 0. So it's easy to see that from the first one, you can elapse at most n time units, and the second one, you can elapse at most m time units. And again, from L1, if you have to do L2, go to L2, you have to do a C, which requires that the value of clock X and Y are both 0. So the value of y has to go to 0, which means you have to elapse exactly n time units and m time units respectively. Okay, but how do you elapse time? The only way to elapse time but not allow the clock x to go beyond 0 is by keep doing b's every 1 time unit, right? But what this basically means that you can do exactly b power m c from this first configuration and go to L2, and do b power m c from the second configuration and go to, again, L2. But you cannot do b power m c from the first one and b power m c from the second one. This is just to say that you have an infinitely many incomparable valuations. So there is no finite simulation for GTAs. And okay, so there is no finite simulation for GTAs, but what would be a simulation for GTA? So if there are no future clocks, we have said that it's essentially same as timed automata. So you could just use an off-the-shelf simulation for history clocks. And for future clocks, as we have just seen, we need to have the values to be exactly same. So no abstraction for future clocks. And this is a simulation for GTA, but it's not finite. And so we have this notion of simulation for GTAs, but it's not finite for valuations. So how do we get finiteness for GTA zones? This is based on the surprising property that for reachable GTA zones, if you only think about reachable GTA zones, the difference between future clocks comes only from finitely many constraints. Just to this bad behavior that we saw in the earlier bad example cannot happen between future clocks. In the interest of time, I will not go into this slightly technical part, and I will just skip to the final logic to automata translation. But just to show that we have the same zone-based reachability picture for GTAs, where we have GTA zones. We have concrete simulation between GTA configurations, but which is not finite, and an efficient simulation test. But the major difference is this finiteness for relation is only for reachable GTA zones, which is good enough for termination because we start with the initial config zone and we only explore reachable zones. Okay, so but we have also implemented this in an open source prototype tool, but probably in the interest of time, I'll skip this as well. So we have this model which unifies several timing features in different models. We have a zone-based reachability algorithm and a prototype implementation. But I will, if I have, do I have 5 minutes? Then if I can, Shubhashish?
You have 10 minutes roughly.
Okay, then I can try to quickly motivate the last part of the logic to automata translation, which is somehow independent of the technical reachability algorithm that I talked about. So if you have, so you can think if you have gotten lost in the talk, I think this is one place where you can come back. Okay, so the last part of this talk is we have introduced this model which captures all the formalisms that we are interested in, but we also said that we want to have a logic to automata translation. So, okay, but how do we do this? So the idea is to extend the logic to automata translation in classical untimed setting by leveraging the powerful features of GT. Okay, so, okay, but what is LTL for people who don't know this? You can check, it's basically, you have the following formulae, which allows you to check whether a proposition is true at a position, but also talk about things that if you are in a state, you can check whether the formula holds in the next position, which is what the first thing, next of phi. You have eventually phi, which says that a formula holds eventually at some point of time in the future. And you also have phi 1 until phi 2, which is what I've illustrated here, which basically says that from this current state, phi 2 holds at some point of time in the future. And until the point where phi 2 is true, the phi 1 holds at all positions until then. Right? This is phi 1 until phi 2, just to give a feel of what this linear temporal logic is. And this analogous notion of metric interval temporal logic is basically an extension of this, which allows you to reason about intervals. So if you think about until, which basically says that phi 1 until interval phi 2, it says that, okay, phi 2 should hold at some position of time in the future. And until that time, phi 1 should hold. Additionally, the time elapsed until you see this witness position for phi 2 should fall within the interval I. So this is the intuition of how we lift this, how LTL is lifted to reason about timing constraints. But okay, let's look at how LTL to automata translation is the most simple translation. And we'll take a very simple formula which says next of P, which essentially asks whether next position is labeled by P. So if you look at this sequence, here is the evaluation of this formula on this sequence. So it is 0 when the next position is labeled by a not P, and it is 1 when the next position is labeled by a P, as you can see. And here is an automaton which provides the evaluation of this formula on a word. So you have two states, yes and no. So yes stores the commitment that next position is indeed going to be a P, whereas no says that next position is not going to be a P. And as you can see here, from yes state, because you've made the commitment that the next position is going to be a P, you can only read a P. Right? Again, from no state, since you have promised that next position is not going to be a P, you can only read not P. Similarly, from any state, whether yes or no, you can predict that you're going to see a P and go to the yes state. If you're predicting that you're going to read a P, you go to yes state and output 1. Whenever you're going predict the next position is going to be a P, you go to yes state and predict output 1. And when you're predicting that next position is going to be a not P, you go to the no state, outputting 0. Right? It's a very simple automata, and I will try to show how we extend this to MITL setting. So let's look at what is the analogous notion of this next in MITL. So you would additionally want to say that, okay, next position is labeled by a P. In addition, it comes from the interval 3, let's say some interval I, for instance, 3, 5. Okay, so what we do essentially is we take the same translation, same construction, and we try to leverage the properties of GTA, check this property. So, okay, what do we want? So if the next position is not going to be a P, we don't care, right? We anyway output 0. But what is important is when next position is going to be a P, in addition, we need to check what is the time elapsed from the current position to next position. And this is what we do using this prediction and validation business. So whenever you do an action, you check that, okay, x equal to 0, which is the validation. And in addition, when you're reading a P, you check, you make a prediction. If the x is in the interval, then you output 1. If your x is not in the interval, you output 0. So we have a future clock x that predicts the time to the next event, which is predicted every time you do an event. And whenever the next event is a P event, you additionally check whether it falls in the interval, and only then output 1, otherwise you output 0. Okay, but how would we do this if we wanted to do it using timed automata? So here you would need 3 states, right? And one additional state, because you have one state which says next position is going to be a P and it's in the interval. You have one state which just says next position is not even going to be P, so we don't care. Additionally, you have this third possibility where your next position is going to be a P, but it's the interval constraint is not satisfied. It's not within the interval, right? So the idea is that if you're translating timed automata, you would store predictions in states, whereas here we are storing predictions using future clocks. So, and in Spirit, it's like, because of you have this efficient machinery of zones for GTA, we are more adept in handling predictions using timing constructs. Whereas if you have predictions in states, you would need additional orthogonal techniques such as things like partial order reduction, which allows you to address state space explosion, which are somehow harder for timed automata, timed models in general. Okay, but this was the final component, which is the logic to automata translation. And to conclude, so we propose a new model that unifies the features of several timing formalisms, such as timed automata, event clock automata, and timers. We have an efficient procedure for checking reachability, which turns out to decide reachability for various models that were before unknown. And finally, we have a translation from logic to automata, which is direct and succinct, which turns out to be somehow more succinct than the state-of-the-art translation from MITL to timed automata. And finally, this combination of all these 3 things results in a new procedure for this model checking for real-time systems. As a part of future work, we would want to implement a model checker that actually does this, because the whole point is to have a framework where you can take any model allow these modeling constructs and take a formula in real-time logic, and then check directly do model checking. And this is something that we are working on, but this requires a lot of engineering effort, the pre-processing of formulae and have efficient parsing of these formulae and get them to work together. And an additional point of interest is what is the exact expressiveness of GTA, the safe GTA. So GTA is, of course, it's a very powerful model, but this interesting class of safe GTA, so we believe we have preliminary results that it's more or less the same as timed automata. So it's more succinct, but same as timed automata. But this is again something we're working on. Okay, thank you. That's all. Yeah, thanks.
Questions? So I have one question, which is, so if you consider MITL, from MITL,
Yeah.
Do a translation to timed automata, or was it something like a one clock alternating?
Yes. So the only the translation from MITL to timed automata had to go to. So what they did was they translated MITL property to weekly 1 clock alternating timed automata. And then, okay, but this is not practical. So what they do is they de-alternate it using this weak property. So it turns out that for the precise structure that they obtain, it's
Using
possible to, sorry,
using what property you said?
the weak property, the weak property of this weekly alternating timed automata. So
Okay.
it turns out that it's possible to convert that into a network of timed automata.
Okay.
But it's so because of these multiple steps involved, you absolutely lose intuition of what is happening. It's possible to de-alternate it, but you end up getting something that has somehow it's very difficult to connect it to the formula. So it's not a direct translation, and it has multiple intermediate steps.
But network of timed automata is also a timed automata, right? I mean,
Yes.
so you get finitely many. So in the network, you have finitely many timed automata when you are
Right. Yes. The weak property essentially says that once you leave a state, so when you whatever weak alternating 1 clock automata you obtain, once you leave a state, you don't come back to the state. Because of this property, they can motivate each behavior of the state, like this weekly alternating 1 clock timed automata by network of timed automata. And this is what is implemented in this the state-of-the-art tool for MITL model checking called MITL.
So that MITL tool, where is it? Like,
So it's by Thomas Briaye, Benjamin Monmej and company.
okay, so you are saying that the languages which can be expressed by MITL, that is a subset of timed automata, essentially. So you have a procedure to translate MITL to timed automata. So timed language.
Yeah. So, okay, I should say that the very paper that introduced MITL by Hensinger, that itself proposed a translation, which was very, very complicated and not practical. But theoretically, there was a translation there around it.
So there was this paper I remember by Joel Worknin,
Yes.
where they had a translation from something to 1 clock alternating time.
Exactly. So that is the very 1 clock alternating time automata translation that I was talking about.
But that
So
was also by that was also for MITL, or was it something else?
it was for MITL.
It was for MITL. Okay.
Yeah. So they initially considered this MTL, which you don't. But MITL is basically a restriction of what you could possibly is a most natural notion of real-time logic, where you prohibit punctual constraints. So you can't say something happened at 5 time units, but you can say non-punctual constraints, like say between you can say 4.9 to 5.1. So basically, this punctuality was leading to undecidability. So if you have this punctual constraint, you can again encode a hard problem. So it's very undecidable. So then Joel Oknin and James Worrell considered this non-punctual fragment, and then they obtained this translation.
Any other questions? Okay, so if not, then let's thank Govind again.
Yeah. Thanks.
Okay, thanks, Govind.
Yeah. Thanks, Subash. Thanks. Thank you all.